Okay, so now we want to talk about free fall, which is really nothing more than constant acceleration motion in the vertical direction. Now, back in the mid to late 16th century, early 17th century, Galileo was kind of the first to propose that objects fall at the same rate. Prior to that, it was believed commonly that heavy objects would fall faster, which kind of makes sense if you were to take like a feather and a rock and drop them at the same time. Obviously the rock would hit the ground first. We could do the same thing with a piece of paper, right? The reason they land at a different time, though, is mainly because of air resistance pushing up on the feather or the piece of paper, and they fall at a different rate. Galileo was the first to kind of propose that without air resistance, objects would fall at exactly the same rate, which we can see if we were to take a ping pong ball and a bowling ball and drop them at the same time, we would see them land at the same time if they're dropped from the same height. You can try this on your own. You take any two objects with different masses and negligible air resistance and drop them from the same height, you're going to see that they hit the ground at the same time. And so what we found is that objects that are in free fall are all falling with the same basic rate of acceleration, which is right around 9.8 meters per second squared. We call this the acceleration due to gravity. Gravity is a force that pulls everything on Earth toward the center of the Earth. And what we'll find is that things that when a force is exerted on something, we get an acceleration. And so in a case of free fall, when you drop an object, it is getting pulled toward the center of the Earth with enough force to accelerate it at this rate of 9.8 meters per second squared. And we're going to talk more about forces later, but for right now, what we need to just understand is that acceleration due to gravity is this value right here. We can approximate that in many cases as 10. We can round that up to 10 meters per second squared when we're dealing with when we don't need to be super precise. Okay, so what we find is we drop an object. After 1 second, its velocity is 9.8 meters per second, and it's fallen a distance of 4.6 meters. So in the next second, between seconds 1 and 2, it increases its velocity by another 9.8 meters per second. So it's going 19.6 meters per second, and it's fallen 19.6 meters. After the third second, so it increases its velocity again by 9.8 meters per second in that next second to be going 29.4 meters per second. And we get a distance of 44.1 meters. After 4 seconds, it's gone another 9.8 meters per second. So now its velocity is 39.2 meters per second, and it's fallen a distance. So what we see is an increasing distance in each between successive seconds, which is accelerated motion. And so what we have here is we have a motion diagram then of an object that has been tossed up into the air from here, tossed up, and then comes back down. Okay, so down here we start out, and it starts out with a high velocity. The thing goes up, whatever it is, we'll say it's a ball, and it goes up and it slows as it reaches its highest point. And for the very briefest of moments right here, its velocity passes through 0 meters per second, and then it begins to fall back down. You have to be very careful here, but you can't think that you can't allow yourself to think that the thing goes up and stops here for a minute and then comes back down. It just kind of passes through 0 meters per second. And then it comes back down. What we find then is that the acceleration, because that acceleration is the same, and we abbreviate that acceleration as g. If we look at this diagram, we can see that the longer arrows are down here. They're toward the bottom end of its path, which means then that acceleration on both the trip up and the trip back down points downward. Okay, so because down is considered our negative direction, it's more precise to say that g, the acceleration due to gravity, is a negative 9.8 meters per second squared. And it's a constant acceleration. So the question then becomes, what does that do to our kinematics equations? So here in our kinematics equations, here's the ones we've been working with. Okay, this has been for one-dimensional motion on a horizontal plane. Okay, so now if we turn that and go in the vertical direction, it's still constant acceleration, but we're using g, our acceleration due to gravity, that has a value of negative 9.8 meters per second. So that changes our kinematics equations to where the first one then becomes Vf equals Vi minus Gt. And then for the second and third equations, we change our position variables from x to a y. Okay, so our second equation becomes Yf equals Yi plus Vit minus 1/2 Gt squared. And the third would be Vf squared equals Vi squared minus G delta Y. And these are all the same equations. All of these here are the same equations as up here. It's just now we're dealing with a negative acceleration that we call the value of g, and we're in the vertical direction. Remember, down is always negative. So then, how do we go about this, right? So let's look at this object here, and we saw this motion diagram a moment ago. This object, we'll call it a ball, goes up. It takes 1.25 seconds to reach its highest point, and then it comes back down to be a total trip of 2.5 seconds. Notice that the time it takes to go up is equal to the time it takes to go down. So that's one of the hallmarks of free fall motion. When we've got an object, we toss a ball up in the air, the time up equals the time down. And it covers the same distance up as it covers down. So then we want to know, how high does this object go? We know that it goes up to some point, and at this point up here, its velocity becomes 0 meters per second at its highest point. At the bottom then, where it started out, you toss a ball up in the air, it doesn't start with 0 initial velocity. It has some velocity greater than 0 when it begins. However, we're looking to know how high it goes, right? So we really don't need this first equation at all, because our displacement is not involved in that equation. Displacement is involved in this third equation, but look, we don't know what our initial velocity is. Okay, we could use the first equation to figure out our initial velocity, and then use the third equation to figure out our distance, or because we know that this is what we're looking for right here is our final position. We know our initial position is 0. We don't know our initial velocity. We do know the time. Okay, so either way we go, if we use the second equation or third equation, we have to first figure out what our initial velocity was. So we have to use that first equation. Okay, so we have Vf equals Vi minus Gt. Okay, because we're using acceleration due to gravity. And what we're looking for is first finding our final velocity, and then we're going to look for our displacement. Okay, so our final velocity, erase that, was 0 meters per second. We're looking for our initial velocity. Our acceleration was 9.8, and we know that it takes 1.25 seconds to reach the height at which the final velocity is 0. So this 9.8 times 1.25 gives us 12.25 right here. So we add that to both sides. We find that our initial velocity then was 12.25 meters per second. Okay, so then what we're going to do is we're going to use that 12.25 meters per second to help us figure out how high the ball goes. Let me just slide that over there. So at this point we can choose to use the second equation, or we can choose to use the third equation, whichever one we'd like to use. So we're going to go ahead and use the third equation. VF squared equals VI squared minus G delta Y. Okay, so our VF, of course, is our final velocity at the up there. So that's 0 squared. Our initial velocity was the 12.25 squared minus 9.8, and we get our delta Y. So the 12.25 squared is 150.1 minus 9.8 delta Y. Solving for delta Y, solving for our displacement then. We get a height of 15.3 meters. So that's how high this object goes. Okay, so then this is for an object, obviously. It goes up and back down. It goes through the same height. So it's going to go, when it goes up this 15.3 meters, it's going to come back down that same 15.3 meters. So this initial velocity that we found over here of 12.25 meters per second is going to be the same as right the instant before it comes back to its initial point. We're going to have another 12.5 meters per second, but it's going to be in the negative direction. Okay? So that's an object that goes up and back down the same height. What about an object that, say, goes up some distance and then goes back down further? So this one here, this is an example right out of the summer assignment. We have a stone that's launched straight up from the top of a building with an initial speed of 7.5 meters per second. How high does it go from the top of the building? How much time does it take to reach maximum height? And if the building's 45.2 meters tall, how much time will it take to hit the ground? I'm not going to actually solve this for you, but I just wanted to talk to you about. You can look at the example in the summer assignment to see how it's solved. But I just wanted to talk to you about some of the particulars of this situation. So when this thing is launched, when it's launched from this height of this building, it goes up at an initial velocity of 7.5 meters per second. It goes up some distance here to where it has goes through a velocity of 0 and then comes back down here. We're ignoring any kind of horizontal motion at all. So we imagine it, however this is launched, a person throws this ball or whatever, they've got their arm stretched over the side of the building so that the ball can go straight up and straight back down along the same y-axis. Okay, so when we go to solve this, it goes up some distance here, and then it comes back down to that same point. So what we're going to do is, if you take this and kind of isolate this portion of it, imagine that portion of that motion is just like the problem we just saw, where it's an up and back down to the same height problem. Okay? And then from this point down, right, we can imagine that this is like an object being thrown straight down from that point. Okay, so let's think a minute. What would be the velocity at this point right here? Okay, well, if we imagine this to be an up and back down to the same height problem, then we know that velocity there is going to be simply a negative 7.5 meters per second. Okay, and so for the remaining part of the problem from here down, we can imagine that as being an object is thrown straight down with an initial velocity of negative 7.5 meters per second. And in both parts of this motion, that acceleration is going to be the value of g, negative 9.8 meters per second squared. So what we can see from this is that, for a lot of problems, we can take and split them up into component problems. Like get a little problem here, we take this little section of it, and then we take this section of it, and then we can combine those two to figure out what we're looking for. And then, of course, as you solve these, use motion diagrams, use And then once the school year starts, we'll look at a couple other ways to model these motions so that we can get an understanding of what is happening with them. All right, so that will conclude the 2 videos for the summer assignment. Continue working through that. Use those websites, particularly the physics classroom one. Really, really good tutorial site there. As well as hyperphysics is another really great one. Great. See you soon.